If you step outside on a perfectly clear autumn night, far from the neon glow of cities, and cast your gaze toward the constellation of Andromeda, you might spot it, a faint ghostly smudge of pale white light. To the naked eye, it looks fragile, almost like a distant cloud of steam frozen in the absolute zero of space. For generations, humanity looked at this smudge and felt a sense of comfort. We called it the Andromeda Nebula, assuming it was merely a small, swirling cloud of gas floating safely inside our own galaxy. The Milky Way. But in 1920, the great debate erupted. Astronomers argued over the very scale of our existence. Was our galaxy all there was, or were there other island universes scattered across an endless ocean of space? In 1923, Edwin Hubble resolved the debate forever. He identified a Cepheid variable star inside the nebula, allowing him to compute its true distance. The math was staggering. The nebula was not inside our galaxy. It was a separate galactic empire sitting at an immense distance of 2.5 times 10 to the power of 6 light-years away. For a moment, this distance brought peace. It was our quiet, glittering sister galaxy, orbiting peacefully in the frozen dark. But as our telescopes evolved, we stopped just looking at Andromeda. We began to dissect it. And that's when the comfort evaporated. We realized we weren't looking at a peaceful neighbor at all. We were looking at a cosmic predator, a silent killer on a direct, unstoppable path toward our home. And the most terrifying part, the forensic evidence shows it has spent billions of years devouring its neighbors. And we are next on the menu. To understand the mystery of Andromeda, we must examine its crime scene. In classical astronomy, spiral galaxies are supposed to be masterpieces of celestial architecture. Elegant spiral arms rotating in perfect gravitational harmony. But when astrophysicists embarked on the Pan-Andromeda Archaeological Survey, known as the PANDAS project, they mapped the outer limits of Andromeda. They expected to find a clean, empty halo of space. Instead, they found a graveyard of devoured worlds. Stretched across the outskirts of Andromeda is the giant stellar stream, a colossal trail of stars spanning hundreds of thousands of light-years. These stars are not orbiting in harmony with the rest of the galaxy. They are moving in chaotic, erratic, looping paths, completely out of sync with Andromeda's natural rotation. How do we know they don't belong here? The answer lies in their chemical makeup. By using spectroscopy, astronomers can measure a star's metallicity expressed mathematically as the ratio of iron to hydrogen. Native stars in Andromeda's outer disk have a distinct, uniform chemical fingerprint, but the stars in the giant stellar stream have a highly enriched, different metallicity. They are the torn, shredded, ghostly remains of entire galaxies that wandered too close to Andromeda's gravitational trap. This is the grim reality of galactic cannibalism. And Andromeda is not a neat eater. Even now, it is performing a slow-motion cosmic heist on the Triangulum Galaxy M33. A massive bridge of stars and neutral hydrogen gas has been ripped out of Triangulum's disk, forming a stellar pathway connecting the two galaxies. Andromeda is systematically dismantling its neighbors piece by piece, pulling their stars into its own halo. But its greatest meal was a galaxy we never even got to see. For decades, astronomers were puzzled by a strange anomaly. Orbiting closely to Andromeda is a bizarre ultra-compact dwarf galaxy known as Messier 32 or M32. It is incredibly small, yet densely packed with stars containing almost no gas or dust. It didn't fit any known model of galaxy formation. Then, in 2018, computer models of galaxy formation revealed a chilling truth. Roughly 210 to the 9 years ago, our local group hosted a third giant member, a massive spiral galaxy known as M32P. It was the Milky Way's slightly smaller sibling, boasting a massive stellar disk. Andromeda ate it. During a violent collision, Andromeda's immense gravitational tidal forces stripped away over 90% of M32P's mass. Imagine a predator eating a piece of fruit. Andromeda digested the vast gas-rich outer disk of M32P, absorbing its stellar material to trigger a massive burst of new star formation within its own disk. The dense, compact bulge of M32P was too tightly bound by gravity to be completely torn apart. It survived the digestion process, cast aside like a discarded pitch pit. Today we look at that pit and call it the dwarf galaxy M32. This single meal was 20 times larger than any galaxy the Milky Way has ever consumed. It left Andromeda with a bloated heavy stellar halo and a thickened disk, the permanent physical scars of a violent cosmic feast. It is a warning written in the stars. We know what Andromeda is capable of because we can see the digested bones of its family. But surely we are too far away to suffer the same fate. For a long time, humanity comforted itself with the sheer unimaginable scale of cosmic distances. We looked at the 2.5 times 10 to the power of 6 light years of empty space between us and Andromeda and assumed we were safe. We believed our world was an isolated sanctuary, separated from the violent physics of our neighbor by a pristine empty vacuum. We were profoundly wrong. In 2015, using the Hubble Space Telescope, scientists launched Project Amiga, the absorption map of ionized gas in Andromeda. Because the gas surrounding galaxies is incredibly diffuse, it cannot be seen directly with conventional telescopes. To solve this, astronomers turn to the most powerful searchlights in the universe, quasars. By measuring how the light from 43 ultra-distant quasars was absorbed as it passed through the space surrounding Andromeda, scientists mapped its circumgalactic medium. And what they mapped shocked the scientific community. The halo is not a small envelope of gas. It is a gargantuan invisible shroud of plasma extending up to 1.3 times 10 to the power of 6 light years from Andromeda and up to 210 to the power of 6 light years in some directions. This halo is composed of highly ionized elements, oxygen, silicon, and carbon. For these atoms to lose so many of their electrons, the gas must be superheated, reaching temperatures of up to 1 times 10 to the power of 6 K. This plasma is being continuously energized by supernovas and past galactic mergers. Because this halo is so immense, it extends more than halfway across the distance separating our two galaxies. And our own Milky Way possesses a similar gaseous halo, which means on a molecular level our galaxies are already touching. The collision is not a distant event waiting to happen in the far-off future. The very outer boundaries of our galaxies have already begun their silent, invisible embrace. As these halos interpenetrate, the gas is compressing and heating up, and the gap between our stellar cores is closing at a terrifying rate.